Good afternoon, everyone. I'm Olivier Wang with École Polytechnique, and this is joint work with my PhD supervisor, Léo Liberty, also at École Polytechnique. And some of you might recognize the name of Christian de Sainte-Marie at IBM France. So I'm going to talk about controlling the average behavior of business rules. The motivation for this work is basically that business rules are used by IBM's clients to model business processes, and some of these business processes are used on a lot of data, on the order of thousands of data points, such as a number of loan requests that might be approved automatically and stuff. So because of a changing environment or changing goals, these clients might want to modify their business process or adjust their business parameters so that they achieve a given goal. And for me, I'm looking specifically at a statistical goal, such as looking to have a given percentage of a yes decision in a yes-no case, for example, among all the data points that they have. So this already exists in a manual form, because you can always look at the number of business rules and change a parameter by hand. But this is always complicated because not all business experts agree, and the people who wrote the business rules might have left the company, and the effects of a change might not also be obvious. So for now, this is a somewhat theoretical work, and I have used a simplified model for business rules. So I'm only looking at linear business rules in the sense that the condition part is only bounding the variable between a lower bound and upper bound, and the action part is only an assignment of a linear function of the variables. So I'm introducing some notations, big P of small p and x, where x0 is the initial data point, is going to be the output of the business rules program, and small f of this value is going to be the actual decision. So I'm limiting myself to a yes-no decision, so 0, 1 output.
Sorry, question. What is the x in the first x if at a time?
So x, it's a vector variable. So it might be basically the notation I chose to use is that you put everything, including, for example, integer variables like the age, and continuous variables like a price, and including yes-no variables like an approval form or something, and then put them in a vector, and basically treat every rule as if the end conditions that affect each part of the variable are basically in a vector form. Yes, and then the goal can be expressed as, in a way, it can be expressed as a bi-objective optimization, but here I choose to use introduce an epsilon to put one of the objectives in the constraints part. So we want to minimize the modifications to the business rules program. So the variation of the parameters P, such that the average decision over a set of input data points is going to be close to a given goal G. So it's a percentage in my case of yes decisions. So to clarify, right, I didn't talk about this part. So the business rules are executed in a loop, and part of my simplification is going to sound very big for some of you, but is that I use the simplest of conflict resolution strategies, where I don't account for refraction, so the same rule can be executed over and over again, and basically there's a fixed priority order on the rules, so it's the order where the rules were written in. And so because of that, so there's also no recency condition. And so because of that, in an example, I don't have a, oh yeah, in an example, so you have the variables. So some of them are going to be modified by the business rules program, but some of them are just inputs. So by variable, I mean both the input data point and the output data point. So for example, if you look at the value of x3, it's never modified by the business rule. And, oops, excuse me. I don't have a mouse, okay. And yes, because I have here a 0, 1 variable, and I test it every time. This is because I don't have a refraction condition in my conflict resolution strategy. So if I don't do that, then I would keep executing the same rule over and over again. So by parameter, what I mean by parameter is a value in the business rules program which can be modified by the business user, but is going to be set to a given value for a bunch of data points. So it does not change between two input data points unless the variable values. So an example here for me would be to evaluate the number of approvals. So the F would simply be the projection on the first variable. And the parameter, I could look at the interest rate, P2, and try to find which interest rate would give me a number of automatically approved loans of about 50%, for example. It must be mentioned that this is, of course, should be lower than the actual number of approved loans that the bank actually wants, because there's always going to be special cases that need to be evaluated by hand. So the way I choose to do it is to transform a business rules program into basically an optimization problem. The thing is, business rules programs, the way I wrote them, are a form of imperative programming in the sense that they modify the environment variables as they execute. And so one cannot use logic reasoning on the static form of this program. To actually use analyze the static form, so I transformed it into an optimization problem. So here it's just a set of constraints. So it's a constraint satisfaction problem that is equivalent to executing one instant of the business rules program on one input data point. So we can see that every part of the business rules program has an equivalent, and here we can look at the indices. So there are basically three indices. I is an index corresponding to the iteration of the loop regulating the business rules program's execution, and R is an index corresponding to identifying which rule we're considering. And the third index is K, because I'm looking at the effective variables. So K is basically x1, x2, and xk. In this particular example, so we see P. We see P here. Okay. P is here, it's not a vector anymore, so it's only a scalar, and the only parameter we want to modify is going to be the first element of the matrix A. Now, using this set of constraints, we actually want to solve our optimization problem. So all we need to do is add an index. So you see there's now four indices. There's an additional J index, and add a goal. So we want to minimize, as I said before, the change to the parameter values. So J corresponds to the data points. So because we want to consider a whole set of data points at once, so in the optimization problem, we need to have every input data at the same time and every execution basically of the business rules program at the same time. The extra constraints correspond to a limit over the number of rule executions in the business rules executing loop. This is because if we don't bound this, the problem becomes intractable because business rules are chain complete. And the second extra constraint is, of course, the goal, so the closeness to the actual objective in terms of a percentage or statistical objective. So because we limited ourselves to linear rules, it means that this exact optimization problem is a MILP. It's a mixed integer linear program, and so there are many existing algorithms to solve mixed integer linear programs. So this is a standard optimization problem formulation, and we can solve this using CPlex or other optimization solvers. The problem with oops, there's an extra column. The problem with this this formulation is that we have actually 4 indices, and that means basically we have a number of extra variables that explodes with both the number of rules in the program and the number of data points we examine. And so this becomes basically too big to solve using usual solvers. So one way of, the first thing we tried to solve this scale problem is to use machine learning techniques, because this looks like a machine learning problem where we have a bunch of data and we have a goal and we want to optimize our value. So instead of using all the data points we have, we restrain ourselves to a smaller training set with a reduced number of data points, which leads to a much reduced number of variables. So to do this, we can use random sampling, or we can reduce the size of the training set even further if we know the theoretical distribution of the input data points. The good thing about this method is that because we get a lot of leftover input data, we can use this data to do a testing set and to check on our value of the parameter and see if it actually gets us closer to the objective. So next I have just a few experimental results. These are very initial results. I just generated a bunch of business rules programs with varying number of rules in each program. So for each number of rules, I had 100 business rules. 100 programs for each number of rules with 100 input data points. And then I restrained myself to a very small number of loop iterations, so 10, because in industrial cases we have often loops that don't actually loop a lot, so we have a limited number of rule executions before we reach the decision. And I chose a 3-dimensional variable. So what we can notice, it's probably more obvious on the curve, is that, well, even with our restraining the set of input data, we have an explosion of the solving time. So the size of the problem is too big to be solved in 1 hour by CPlex, basically, even with, as you can see, with 4 rules, so that's not at all an industrial rule set. It's already too much. the last experiment we ran was to look at the value of epsilon, so the closeness to the goal, the statistical goal. And so what we see is that it's actually working pretty well in the sense that for about 0.6, so that's less than 10% of the available values of the variable x, because x was between -5 and 5, then we have a majority, like 0.7, so 70% of basically a random business rules program can be solved. So to finish, I'll just resume, go over what I said. So average behavior can be controlled via optimization problems. So this applies for business rules programs, but this could also apply to basically any program. So it's a kind of program analysis method. If we have linear rules, then we can model with a mixed integer linear program. That's important because these are somewhat the simplest kind of optimization problems we can find. Even simpler would be to remove the integer part, but that's not doable because with rules we have yes-no conditions. And so solving is a problem. So there are other solving methods. And so a potential solving method would be to look at it as a bi-optimization problem, bi-objective, optimization problem. And so use different methods, such as what do you call this? Separating the two objectives and dealing with each of them one by one. Or maybe even, like I said, trying to solve it as an LP, so as a linear problem, and then looking at, so using the relaxed form of the MELP, and then trying to see if the solution we reach is actually valid for our business rules program.
Thank you.
What extent is actually about business rules, and to what extent could be also used for other domains like science? So I think it's more numerical optimization.
So what you mean other domains such as inference rules or so the big difference between business rules and inference rules is that you can't reason statically over business rules as easily. And in fact, there are probably easier methods to do such things over domains that accept logical reasoning, such as inference rules. For business rules, I liken them more to things like actual programming languages, such as Java or Fortran. So imperative programming, where you modify the environment variable state, and so it's harder. You need to look at the semantics to be able to do logical reasoning.
So maybe the following is equivalent to when you're programming algorithm search space, but it seems to me that once you try to use the dependency structure in terms of backchain depth of dependency depth of logical dependence to set up the problem essentially as a kind of iterative or recursive set of Lagrangian multipliers, because you're starting in the neighborhood of the current rules, whatever they are, and then you could do perturbational analysis about how much more likely are you to satisfy a certain rule given the data that you have. If you tweak the parameter up by a certain amount, and you can define, do that at different brain sizes, start coarse and go finer. In other words, you could leverage the logical structure, and you also probably could then inject information from people about which parameters is it more plausible to change.
Yeah,
there's probably
so
some knowledge
this is the
behind
problem.
why
Yes.
the parameters are the way they are. So you don't want to just mess with them randomly. I mean, certain things
Okay,
like
so
screwing with the age bracket to go under 18 might be pretty significant for other viewpoints.
So,
you know,
yes,
to just make more instances get satisfied.
That's true.
Like that, right?
So the first thing is the parameter is not chosen by the program, it's actually chosen by the user. So this is relevant because some parameters can be changed, as you pointed out, and some cannot. So some might arise from regulations and internal policies, and so it's obvious that when there are a bunch of parameters you can change, you might want to point to the best one. But it's not always the case that there are many parameters you can change. The second thing is looking at backpropagation is not so easy when you look at many executions at the same time. So because the logical chain is particular to one execution in the sense that, well, looking at the logical chain of every execution is about the same as executing everything. And I don't know how easy it would be. I think it would be about the same complexity to actually modify, to look at the inference over every single result, or the average number of results of a single modification of a rule.
I see what you're saying. Well, I don't know. My intuition is that you could, take a dynamic programming approach on that, and maybe it's probably because of the algorithms that iLog uses that you see. Right?
Yeah.
You get iLog business rules, which has working memory, but it's not really keeping track of dependency structures. The way, for example, table logic program methods do instead of ergo or XSP or something like that. Because there, then you could basically analyze which subset of the set of successful or unsuccessful bindings would change based on a parameter and store that too. And because that information, that would save a lot of work in terms of computing. You don't have to be computing every
Yeah, so ideally I want to combine the two. Yes. Yes, ideally I want to reduce the number of combinatorial possibilities by looking at this. So I don't think you can solve the whole problem just by doing that, is what I meant.
Well, we can talk
Yeah, yeah.